Okay, so Chapter 2 study guide. We're going to start by refreshing our memory that it is always a good idea to show your work on a test. And I realize that some of these there's not much work to show, but as much as you can, show your work. An incorrect answer with appropriate work could get partial credit, so it's always a good idea to show me that you understand things. If you make a minor mistake, you're going to get most of the points. I remembered to bring home some tracing paper, so I'm going to trace these two triangles separately. If you just draw them in your notebook, that would be a strategy. Now I'm separating them when I draw them because there's a lot going on in this one diagram. Lots of triangles, and I want to be able to choose the correct shortcut. So these posters are on the board, and they're also summarized in the math notes that are on that are in lesson 2.1.1. So if you are using the ebook, go to lesson 2.1.1 and scroll to the bottom. So if I trace these two triangles separately, I see, and I realize this is not okay. I think it's getting a little bit better. I have three sides in one triangle because this side that's shared is congruent to itself. So I've got three sides in one triangle congruent to three sides in another triangle. I know this has kind of got a glare to it. There we go. So that shortcut would be side, side, side. If all three pairs of corresponding sides are congruent, then the triangles are congruent. And if you want a refresher on what we did with the e-tool that day, there's a video on Google Classroom showing all of the shortcuts using the e-tool. If you're wondering why does this work, you could even use the e-tool. I show you how to get to it from the CPM website and kind of play around with it again. Or you can just rely on the posters and the math notes, but definitely I would review that video at least once. Okay, so then these two triangles would be congruent by SSS. And if I was showing work on this, maybe just highlight, let's see, put this underneath, highlight the two triangles that we're focusing on. Okay, those two triangles are the ones that are congruent by SSS, and maybe add the markings for that third side. So all of these diagrams have the same shared side. So over here in these two triangles, we've got that same side that's shared. Okay, if I trace these separately, that gives me, and I know this tracing paper is not showing up too well on the camera, so I'll kind of tilt it, get rid of that glare. I usually do my videos during the day and don't have too many issues with lighting. If you look at these two triangles, you have a pair, and what we did in class is we wrote down what was congruent. So you have a pair of sides. That would be a good way to show your work. You have a pair of angles, and you have another pair of sides. So you've probably already guessed that these are congruent by SAS, and let's just read this together. If two pairs of corresponding sides are congruent, which we have in our diagram, and the angles between them, so the angle has to be in sides for SAS to apply. If it wasn't, then that would be side side angle, or angle angle side, which spells in an appropriate word, and that is your reminder that, oh wait, that doesn't guarantee that triangles are congruent. So if the included angles are congruent, then your triangles are congruent. So if you look at this picture, that's exactly what we have. And if it's throwing you off that everything's kind of put together in one picture, you could just separate them. And then if you didn't have these in the right order, I happen to write them in the order that the shortcut is written, you would just have to ask yourself, is the angle that I'm looking at, is it in between these two angles? Is it included? And if it's where those two sides meet, then yes, that's the included angle. Okay, let's keep up with writing this out. This one, you would just write side, side, sides if you were writing out what's congruent. Okay, looking at these two triangles, we've got that shared side, so we've got a pair of sides. We've got a pair of angles. We've got another pair of angles. Now, you're probably, I'm writing these kind of in the order that they're supposed to be in, but if they weren't, if you had put the side in between and you had written angle, side, angle, that would have been incorrect. This is actually angle, angle, side, or side, angle, angle. It doesn't matter what order you write that in. So let's look at that in this math notes. So angle, angle, side, if two pairs of corresponding angles and a pair of corresponding sides that is not between them are congruent, then the triangles are congruent. So see how this side, it's not in between these two angles. If it was included, it would be like this picture, angle, side, angle, but it's not. So that's angle, angle, side. Two angles and a side will always work as long as there's nothing tricky going on. But if you had put angle, side, angle for this one, you would lose some points. So angle, angle, side, or side, angle, angle. This side, I'm trying to get the lighting so you can see the answer. This side is not in between the two angles. If it was the included side, it would be this side or this side. Okay, next we have, let's see. Okay, next we have an angle, a pair of angles, an angle congruent to an angle. Let's see, there we go. And then we've got another pair of angles congruent, and we've got that shared side. So let's mark that on the tracing paper, and let's write down what we have. We've got a pair of angles. We've got another pair of angles, and I'm purposely writing it like this, and we've got a pair of sides. Now, is that side, is it included in between the two angles? Yes, it is. So the answer would be angle, side, angle, not angle, angle, side. So let's read that one together. If two pairs of corresponding angles are congruent, two angles congruent to two angles, and the corresponding sides between them are congruent, then the triangles are congruent. So if you had put angle, angle, side, or side, angle, angle, you would have gotten this one wrong. It's actually angle, side, angle. And if you're needing more practice with this, the con is not super helpful con assignment with this because it doesn't force you to pick the shortcut. I was actually thinking I was planning on making a video today with all of this, and I just didn't have the time. But actually, I think this little part of this study guide video is going to be a good review for you. And then I could pick out some problems from the book if you wanted more practice. Okay, now let's look at these angles here. We have a pair of sides. We have another pair of sides. What else is congruent? You should recognize that you've got intersecting lines. The angles that are across from each other are vertical angles. If I were to trace this angle, and rotate it around, it would be the same as the angle right across from it. So those are congruent. So let's mark those angles. That is a pair of, ooh, that's a little bit better. That's a pair of congruent angles right there. So then we've got a pair of angles. Now, two sides and an angle. That only works if you have the angle in between the two sides. If two pairs of corresponding sides are congruent and the angles between them, that angle has to be between the sides, that's called the included angle, then my triangles are guaranteed to be congruent. There's no way I can make this one different from this one if these are locked in place, these angles and these two pairs of sides. So is this angle in between the two sides? Yes, it is. So these would be congruent by side angle side. Okay, let's look at this picture. We've got the same vertical angles congruent. We have a pair of angles. We have a pair of sides. We have another pair of sides. Okay, so if I spell this out, that should remind you of something. That is not a shortcut. So two sides and an angle only works with side angle side, angle side side, or side angle angle. If you're wondering why this doesn't work, watch the video that I put on Classroom showing all the different shortcuts using the tool, e-tool, because I have an example of this configuration, and we were all, well, maybe not everyone, but most everyone was able to make two different triangles when we set it up with these parts locked. And you could play around with that e-tool. This is the one that doesn't work. Almost everything else works. Well, not everything, but a lot of the other configurations work, but this one does not. And fortunate for teachers, it's the one that's a bad word. Okay, so number 2, we have two right triangles right there. That should make you think, oh, this might be hypotenuse leg. So I've got a pair of angles that are congruent, and I'm noticing that these are right triangles. Right there, I'm going to say, is this hypotenuse leg? Hypotenuse leg says if the hypotenuse and a leg of one right triangle are congruent to the hypotenuse and a leg of another right triangle, then the triangles are congruent. Because if I can find the missing side in a right triangle, which I can using Pythagorean theorem, then this side is going to have to match this side. So this really is just another version of side, 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 or you could think of it as side, angle, side, with the angle being the right angle. So hypotenuse leg is potentially going to be the answer here. Do we have a pair of hypotenuses that are congruent? Yes. Do we have a leg that's congruent? Yes. So this one you do have to write out the statement. So I'm going to write triangle ABC is congruent to, and it doesn't matter how the position or the order in the first triangle, but the position of the letters in the second one has to match the first one. So if A is my right angle, that corresponds to F. F has to go first. B, if I were to trace this triangle, and if you're not sure, just trace it. Until if I'm writing on the right side. Mark everything. These are pretty easy if you just take your time. Okay, to map this triangle onto this triangle, I would reflect it over a vertical line, and I can see A matches with F, B matches with D, C matches with E. So that's going to be triangle F, D, E. The reason that they're congruent, hypotenuse leg. Okay, last but one on this page, we've got a pair of angles that are congruent. We've got a pair of sides, and we have another pair of angles. Now these are right triangles, but we don't have hypotenuse congruent, so I know it's not going to be hypotenuse leg. So let's see if this is angle side angle. Angle side angle says if two pairs of corresponding angles are congruent and the corresponding sides between them are congruent, then the triangles are congruent. Let's see if we have this configuration. Well, we've got two angles congruent to two angles. We've got the sides in between them. So yes, they are congruent by angle side angle. So it doesn't matter the order I write this one. I could say RQS. And this one's kind of nice because the angle R is marked, and it's marked congruent to T. So if R is first, T has to go first. Q is my right angle. It's second, so U has to go second, and then V would be last. Okay, that was a lot, and you probably, I know many of you don't necessarily have enough practice with this because we are going quickly through this chapter. So take advantage of the other video. Maybe just go through this another time and practice and see if you can get the answer without me explaining it, and then check and see if you got it right. Okay, number 3. Let me grab some graph paper. Okay, if you need to pause the video for a second, this number 3 is going to require I would use an entire sheet of graph paper. So you're going to graph these points and enlarge the original figure by a factor of 3, and then you're going to label it A prime, B prime, C prime. So pause the video, graph your original triangle, and then pick up at this point. So we're enlarging by 3 from the origin. So if we're enlarging from the origin, that does make life a little easier because I can just multiply the coordinates by 3, or whatever the scale factor is. So my center of dilation is the origin. There's a ray going through the origin and this point, and if I'm multiplying by 3, then I'm going to multiply the rise by 3 and the run by 3, or I can just do 3 times 3 is 9 and 2 times 3 is 6. So then my new point would be at 4, 5, 6, 7, 8, 9, 1, 2, 3, 4, 5, 6. Okay, so that's going to be C prime. This would be -6 and +3. Did I do that right? 3, 4, 5, 6, 1, 2, 3. Okay, there's B prime, -6, +3. And I mean, you could do the rise and run. It's just kind of easy to just multiply, but if you wanted to, you could just say, okay, my rise is 2, so I'm going to multiply that by 3 and make it 6. 2, 4, 6. My run is 3 if I'm starting at 0, 0. So instead of going over 3, I'm going to go over 9. That's another way to think of it. Okay, B prime, and then A prime, I'm going to put at -9, 4, 5, 6, 7, 8, 9, and -6. 4, 5, 6. So there's A prime. And this should look 3 times bigger than your original rectangle. Your original triangle. When you dilate an image, those corresponding sides, they're either going to be parallel or they're going to be on the same line, and your angles are going to be congruent. So not too difficult, but you definitely want to practice so that you get this right. Okay, number 4. Pentagons ABCDF and JKLMN are similar, but not necessarily drawn to scale. Find the values of X and Y. Okay, well, if these are similar, we know that the angles are congruent and the sides are in proportion. So that means whatever I do to this side to get the corresponding side in this pentagon. And yes, it is 30. I did orient them the same way, but you shouldn't think that they will always be oriented the same way. Maybe it was a translation. It could have been a reflection. So I'm going to check this order here before I make that assumption. So whatever I do to one side to get the new side, I'm going to do the same thing to all of these sides to get the new side. So let's check the order here. AB corresponds to, if you look at AB, first two letters, JK. So it looks like, yes, this orientation, it was just a translation, no reflection, just a dilation. So BC definitely corresponds to KL. So whatever I do to 5 to get 30, I'm going to do the same thing to X to get 36. And I'm going to do the same thing to 4 to get Y. Now there's several ways to do this, and different students like different approaches. As long as you show me your method, then we're good. So I'm going to set up a proportion, but if you want to just draw arrows or show me in a different way, that's fine. So I'm going to say that, and I'm going to do this kind of a long way because some students might benefit from this, but if you're like, Miss, I know how to get the answer, it's not that hard, that's fine. This just might be helpful for some people. So if you take A, B, C, D, F, and it's similar to J, K, L, M, N, you can write out the ratios for all the corresponding sides. AB corresponds to JK. And that, whatever that ratio is, whatever that reduces to, BC over KL is going to reduce to the same thing. Okay, and I'm just going to go down the line. CD, let's see, LM, DF, MN, and then FA. We're not done here because it's a pentagon, so 1, 2, 3, 4, 5 sides, FA, and NJ. And then you could just plug in what's given. So they give you AB is X, JK 36, BC is 5, KL is 30. Now CD, I don't know, LM, I don't know, so I'm just not going to worry about it. DF is 4, MN is something I'm looking for, Y. Okay, and then I don't know FA and I don't know NJ, so don't worry about it. And then I'm just going to solve for X and solve for Y. Now some of you are going to cross multiply and divide, some people are going to do it different ways. Just show me your work and you'll be fine. So I'm going to cross multiply and divide here. I'm going to do 36 times 5. And then X times 30, and then I'm going to divide both sides by 30, so X equals 6. Now I'll do it the short way in a second. Then I'm going to use this proportion. So when you have two ratios that are equal to each other, this is a proportion. And I'm going to say 5 over 30 equals 4 over Y. 5 times Y, 30 times 4. Divide both sides by 5. So Y equals 24. Now, some of you are going to look at this and say, okay, if I know 5 corresponds to 30, I'm just going to say, I know 5 times 6 is 30. So I know that 4 times 6 is going to give me this answer. That's fine. 4 times 6 is 24. That's perfectly fine. Show me the arrows. Show me that you knew it was times 6, and you're good. And then going backwards, be careful here. I know I'm going backwards to go from 36 to X. So in that one, I would do 36 divided by 6 instead of times 6. Or I could just say 6 times what is 36? So X equals 6. Okay, number 5. These shapes are similar, but not necessarily drawn to scale. What's the value of Q and R? Okay, now here, this is more than just a dilation. This has been rotated and maybe even reflected, I'm not sure. And in this case, I'm wondering, would it be better to do the long process? UV is to AB. And we're not going to use all these ratios, but it guarantees that you're going to set things up correctly. VW is to BC. WX is to CD. Just look at that last letter and pick up where you left off. So XY is to DE. And what's next? YZ is to EF. Almost done. ZU corresponds to FA. Okay, I know that's a lot to write out, and some of you might get it without doing all of this, but in case you need it, it's here. So UV, I don't know. AB, I don't know. VW, don't know. BC, not there. WX is 9. Okay, so let's put 9 over CD is R. XY is 12. DE is 40. So it looks like maybe it was just a rotation. In which case you could use tracing paper to just see which sides correspond. But not everybody finds that easy. YZ is 3. EF is Q. ZU, I don't know, and FA, I don't know, so we're not going to worry about that. So it's the same process as the one we just did. So I'm going to cross multiply and divide to solve for R in this proportion. That's going to give me 360 equals 12R, and if I divide by 12, R equals 30. And then I'm going to switch over and look at this proportion. So 12Q equals 120. So divide both sides by 12 and Q equals 10. Could you have done it without all of this? Yeah, you probably could have. Some people will just figure out the scale factor by figuring out that XY corresponds to ED. And I would just double check with the statement and make sure you've got, you know, like if you're using this as your basis to get the scale factor, like check and see, does XY, is it in the same position in this one as DE is in this one? And yes, they are. X and Y are the 4th and 5th letters, D and E are the 4th and 5th letters. So then we know that those do correspond. That if it's written like that in the directions, then it's telling you which ones correspond. So some of you will just do 40 divided by 12 to get the scale factor, which is 3.3 repeating. And then now this is going to be a little bit tricky because if you do 9 times that, well, mine rounded off to 30. I was thinking you might get 29.9. And then if you want to just do 3 times, oops, 3.3333. So that's the one thing you have to be careful of, but I'm sure you would know to round off in that case. Okay, looking at number 6, we're given that SE is to ET, so SE to ET is the same as ME to EP. Okay, so that's saying that the sides are in proportion. That's saying that whatever I divide SE by ET by, I'm going to get the same thing when I divide ME by EP. That means that these have a common scale factor. how can you justify that triangle SME is similar to TPE? So if this side divided by this side is the same as this side divided by this side, and you've got the angle included in between those sides congruent, those are vertical angles, then these two triangles would be similar by SAS. There are just like there were shortcuts for congruence, there are shortcuts for similarity, and they are summarized, and you probably want to review this because we are going really fast through the end of this chapter. They are summarized in, I'm going to find it. It's in lesson 2.3.2. And there's only 3 short for similarity, not as many as there are for congruence. So 2.3.2, conditions for triangle similarity. Angle, angle. If 2 pairs of corresponding angles are congruent, then the 2 triangles must be similar. If these 2 angles are equal to these 2 angles, that third angle has to be the same, and then it's just a dilation. Side angle side is also a condition for similarity. If 2 pairs of corresponding side lengths have the same ratio and the included angles are congruent, then the 2 triangles must be similar. So that angle that's congruent has to be between the sides that are in proportion, just like in SAS for triangle congruence. So they give you an example here, just like the one we just did. And then SSS, if I can multiply A and B and C by the same amount and get the new triangle, then these 2 triangles must be similar because their sides are in proportion. There's no way they could not be, one could not be a dilation of the other. So take a minute and check those out on the ebook. And then you're using those for number 7. Determine if the triangles are similar, state the reason, if not, say why they're not similar. So here you've got a 72-degree angle and a 90-degree angle. So if I do the math here, I know that these add up to 180, so 90 plus 72 plus x equals 180. I'm going to solve for x, so I'm going to add these 2 together and then subtract 162 from 180, so x is going to be 18. So this angle is 18, which corresponds to this angle. So then if this is 90 and this is 18, this must be 72. So yes, these 2 triangles would be similar, whoops, by angle, angle. Okay, part B. I'm going to do the same process and see if we've got 2 angles that are equal. I know that these 3 angles add up to 180, so 25 plus 90 plus, whoops, plus x equals 180. 25 and 90, that's going to be 115. So then this missing angle is going to be 65, not 55. So be careful. If you were just glancing at this, a lot of students will say, oh yeah, this must be 55. But 65 and 55 adds up to 90. Plus 90 would be 180. So I don't have a 55-degree angle here, so then these 2 triangles cannot be similar. If they were similar, they would have, their angles would be the same. For part C, I see that I have 2 sides and an angle that could potentially correspond to these 2 sides in this angle. So let's check this out. 5 times 2 is 10. 6 times 2 is 12. So the sides are in proportion. 5 divided by 10, or 10 divided by 5, is the same as 6 divided by 12, or 12 divided by 6. It doesn't say which one's the original. So, and then we've got the angle in between those 2 sides that's equal to this angle. So yes, these are these two triangles are similar by side angle side. If two pairs of corresponding side lengths have the same ratio, which we just saw, and the included angles are congruent, then the two triangles must be similar by SAS. Okay, part D. Let's see what happens when we compare the ratios of these sides. Now, you might have said, how did you know 5 was going to correspond to 10, 6 is going to correspond to 12? How do you know it wasn't 10 over 6 over 5? You can try that. 10 over 6 is not going to be the same as 12 over 5, so then you could try what we did. And one of those options, if one of them works, then you have to say, well, they must be similar. So if these are similar, then the smallest side here is probably going to correspond to the smallest side here. So I'm going to check out and see if 9 divided by 3, or I could do 3 divided by 9, is the same as 4 divided by 12, or 12 divided by 4, and then 5 divided by 15, or 15 divided by 5. Well, this is going to reduce to 3. Did I do that right? I put 9 over 3. And I put 3 over 9. Oops. This should be 9 over 3. And this should be, or this should be 3 over 9. And this should be 9 over 3. Okay. Hopefully I didn't totally confuse you there. But I'm going to check and see what these all reduce to. This reduces to 1/3. This reduces to 1/3. And this reduces to 1/3. And the nice thing about our calculators is that they reduce to lowest terms. They don't automatically change it to a decimal. 9 divided by 3 is 3. 12 divided by 4 is 3. 15 divided by 5 is 3. So this is kind of a straightforward example of side, side, side. Or, I mean, I could, because it's got the angle there, the right angle, I could say side, angle, side. But let's just review side, side, side. If all 3 pairs of corresponding side lengths have the same ratio, then the two triangles must be similar. So if you can multiply all 3 of these sides by the same scale factor to get the new triangle, you've got similar triangles. So let's put similar by SSS or SAS. Okay, number 8. Are these two figures similar? Just realizing this came out kind of crooked. If so, describe the series of rigid transformations and dilations that map figure 1 to figure 2. Well, tracing paper is going to be your friend here. First, let's see if they're similar. We're not making an assumption if we say that these are right angles. So, get a marker. Let's put this underneath. Okay, so we are not making an assumption if it's on the coordinate plane that this is a 90-degree angle. So we do have a 90-degree angle here and a 90-degree angle here. Let's trace, oh, maybe this would show up better with a marker. Let's trace triangle ABC on our tracing paper. And let's see what transformations we're using. Well, first let's see if they're similar. Look at the length of this side. This side is 3. This side is 1, 2, 3, 4. It's not 5. You're not counting the lines, you're counting the spaces. Now I could use Pythagorean theorem to find this. If I do, I'll get 5, but it's not really necessary because I'm noticing this side is 1, 2, 3, 4, 5, 6. This side is 1, 2, 3, 4, 5, 6, 7, 8. So I'm noticing that if I multiply 4 by 2, I get 8. And if I multiply 3 by 2, I get 6. And then I've got the right angle in between those two sides. So yes, they are similar. by side angle side. Now if you wanted to, you could do Pythagorean theorem. You would get that this is 10, and you could say that they're similar SSS, but if you do that, you would have to show the work that you got the hypotenuse. Okay, let's describe a series of transformations. If I were to, let's put our right angle on here. Oops, 3 and 4. Okay, if I just rotate it, it's not going to map on top of this triangle, because I bet you're thinking, just rotate it, but if you do that, A is down here. So it's going to be more than a rotation. It's going to be I'm going to need to reflect this. So let's reflect it. Now, I would say reflect it over BC and let it land right there. So reflection over BC, and then let's go ahead and translate it down too, so that this vertex C corresponds to C prime. Then let's rotate it either clockwise or counterclockwise. Is this going to work? Oh, you know what? I think we need to rotate it, or reflect it again. Hold on a second. I think I did something wrong. Okay, I see what I did wrong. Let's translate it. I was looking at this C and this C, but if I bring down this C, it's on top of A. So let's bring down vertex C. I think that is, that's 1, and then this is at 2, 4, 6, 7. So it's going down 8 units and right 8 units. So that C is coinciding with C prime. It's actually C double prime because there's more than one transformation, and then rotating counterclockwise 90 degrees. And then there would be a dilation. So let's write that down. So that started with a reflection over BC. Okay, and then translated, let's make sure I'm getting those units right. This went from being at 1 down to 7. So down 8, right 8. Okay, so translate down 8, right 8. And you might be able to do this differently than me. You don't have to do it the exact same way. And then we rotated (90 degrees) counterclockwise to get our corresponding vertices to line up. So rotate 90 degrees counterclockwise. Okay, that is number 8. Number 9, what's the area of the shaded region? So here we have a triangle. The larger shape is a triangle, and this is why I assigned those assignments on area of a triangle and area of a rectangle. Hopefully that was easy for you, but if it wasn't, I hope you feel like you're up to speed now. So I'm going to find the area of the shaded region by doing the area of the triangle. This is something we would have spent a lot of time on if it was geometry, but they expect you to know this at this point. Minus the area of the rectangle, because I want this. I don't want the area of the rectangle, so I'm going to subtract it. So a triangle is base times height divided by 2. A rectangle is just base and height. So the base and height of my triangle would be 54 and 18. So 54 times 18 divided by 2 minus my base and height of my rectangle would be 5 times 16. And I'm just going to leave it like that because I want to see that you did the work. I'm not necessarily super interested in seeing if you can type all of this in your calculator. I would like to see this. And then if you want to go ahead and write the final answer, that's fine. Here we have a shaded region where the part we want, now there's more than one way to think of this one, but I'm going to think of it as the area of a rectangle minus the area of this triangle, because I don't want this, so I'm going to subtract the area of the triangle. So the rectangle would be base times height. The triangle is base times height divided by 2. So my base for my triangle is 27. Oh wait, let's do the rectangle first. The rectangle, the base is 27, the height is 8. So 27 times 8. The base and height of the triangle would also be 27, and the height of that triangle is not drawn, but it would be the perpendicular distance from this vertex to this base of the triangle. Any side of a triangle can be the base. So that would be 27 times 8 divided by 2. If you decide to figure out this final answer, just be careful that if you're typing it in all at once, I would put parentheses here. Same thing on this one. Do parentheses just to make sure that you're getting the correct answer. Number 10, what's the area? That should say area of this figure. And we are not going to be able to get an exact answer because all we have is that this length is 10. So there's also no right angles here, and there should be some right angles. So let's go ahead and put those in. I think it was actually like that on the district test. But if I did the area of this rectangle, it would be 10 times whatever the length of this side is. Well, the length of this side is the same as the length of this side. So from here to here is, well, this distance right here is x. This distance right here is x. And this distance right here is x. So then this length is 3x. X plus x is 3x. So the area of the entire rectangle, including this part right here, is 3x times 10, which would be 30x. I don't want this little piece right here, and I know this doesn't look like this side is equal to this side. It's kind of hard for me to do that sometimes on the computer. So I'm going to get rid of this by subtracting x times x. It doesn't really look like they're equal, but close enough. So the answer would just be 30x minus x squared, and that's as far as you can go on that one. Okay, review this a couple of times before the test, and if you can do it without looking at the video, you're in good shape.